laboratory. Diastereomers are dimensionally different stereoisomers, with always having different properties under all conditions. Enantiomers are more subtle in terms of their differences. So if I had, yes?
The enantiomers have the same physical properties, like melting point, boiling point?
If the interaction with the environment is symmetric, then it can't, the environment can't distinguish between the two. It has to be a hand in a glove and not a hand in a mitten type of interaction. But diastereomers are always recognized as different by melting, boiling, everything. So it's much easier to deal with diastereomers. You can separate them using any conventional method, recrystallization, distillation. And if I gave you in a bottle all four of these stereoisomers, you would probably initially think that it's just a mixture of two. You've got this one, well, this one is a diastereomer of either one of these, and this one is a diastereomer of either one of these. So even though there are four compounds in there, it would appear that there are only two. So if you did gas chromatography, for instance, you get two peaks, because the enantiomers are masquerading as a hidden pair of isomers. It would only come out in a chiral environment. And by the way, we do have chiral gas chromatography with certain types of columns that have a chiral stationary phase. Then you get four peaks instead of two. So just to finish with one compound here, if you had a compound like this, a common question on a test would be identify each of the asymmetric or chiral carbons, be the same thing in this molecule. So you would of course forget any CH2s or CH3s or double bond carbons or triple bond carbons. You'd hone in on carbons that look suspiciously like they might have four different groups. In an open chain segment of a molecule, you can use that simplistic rule of four different groups. So those two carbons are clearly asymmetric using that first rule I gave you, that an asymmetric or chiral carbon has four different substituents. HCl, CH3, and then the whole rest of this, HBr, CH3, and the whole rest of this. But you have two ring carbons that could be asymmetric. That's to draw in those two substituents that are different, clearly. So now you have to go to this more sophisticated rule for cyclic compounds, which is draw a plane of symmetry one at a time now. Don't try to do them both at the same time. Pick one, draw a plane, forget the H and the other thing there, just draw a line bisecting the carbon that you think is asymmetric and the rest of the ring. So is that an asymmetric carbon at 12 o'clock? Clearly, yes. And you can guess, of course, that if you do the same thing here. But now remember, that involves a different plane of symmetry through the new carbon that I think is asymmetric, and then perfectly bisecting the ring, which would be at a different angle through that ring. And then, of course, the two halves are different. So this one has four asymmetric carbons. 2 to the 4th is 16 different stereoisomers. That's not unusual at all. There's a very powerful anti-cancer drug for breast cancer called Taxol that has 16 asymmetric carbons in it. And only one of the 2 to the 16th power stereoisomers is a chemotherapy agent active. So this is very